Okay, welcome everyone to today's session. So in our today's session, what we are doing is, so we are discussing the models under heteroskedasticity that we discussed earlier in detail. So we are studying the case when the dependent variable is not normally distributed. Not normal means that what were the properties of a normal data? That it is a continuous data, and it is a continuous data where what you call it, all possible values can occur, and there are no gaps between the data. So these are some properties of data. So first of all, what we'll do is we will pick up an example and I will describe the example, and then we'll see that what will happen if we run simple OLS on it, so that we can see what are the problems, and then we'll go towards possible models. So in our first session, I'm loading following libraries. So usually when the libraries are there, when you run it, Control plus enter, it will load automatically. But if the library is not installed already, it will say that the library name is not found. So you have to install it by going here, install packages. There you have to write the library name so that you can install it. So I have written descriptions in front of each library code. So see, all the libraries have been loaded. So I will give you a brief overview of what kind of errors it can give, what are serious errors and what are not serious errors. So when I loaded the inspect.df library, it is said that the package is built under R 4.03, 4.0.3, and my R that I have installed is 4.0.1. So it means that it will work better if I have the advanced version, but this error will not hinder our performance. This library is also built for advanced version, but still it will still work. This library tidyverse has several sub libraries, but it is also saying that in few libraries there are few conflicts with already loaded libraries. So you have to remember that if you have to use these libraries like extract, then you have to add tidy r colon colon, otherwise it will confuse related to which one is it. So is it extract from past text or extract from tidyr? So I will give you examples later on. So all these libraries are for advanced version, and then there's deployer. Deployer is already loaded, that's why it's not showing anything. Now we'll go towards loading the data file. So once you already load, the code is shown, then you can just Control plus enter and load the data file. So I have opened this data file and let it load, and then we'll see what type of data it is. Then we'll go towards this analysis. So this data is loaded. It has 26,000 observations. So first of all, what I will do is, first of all, I will show you the data file. In this data file, let me make it bigger so that it is viewable like this. So the variables, it is the questionnaire based data. Here the age of the respondent, household size, gender, education, if they are migrated, their house hours worked, and if he is poor or not. 0 means not poor and 1 means not poor. Does he have a holiday in the contract? Then educational variables. So this is the data of questionnaire based level. So the dependent variable that is selected in this study is poor. So this data is binomial. It has only 0 or 1. So let's see what happens if we try to estimate this model. First of all, I will run this command so that I will remove the NA values in the dependent variable so that my data becomes shorter, because the regression will never use a data where the dependent variable has missing values. So I will run it, and the data is shortened to 14,000 observations. Now what I will do is we'll see its descriptions. So the command is stat.describe and the data file name If I run it, it will give me detailed descriptive analysis. Here you can see that for each variable, it is giving me number of values, observation, number of null values, number of NAs, minimum, maximum, range, sum, median, mean, standard error, confidence interval 95%. Then then there's variance, standard deviation, coefficient of variance. So all common diagnostic, the descriptive stats that you need are here. So you can do a descriptive statistics from these commands. Then you have to know before regression which all the variables are string, which are numerical. So it's str.df, comma df. So when I run it, it tells me that all the variables are numeric in the data. So all variables are showing its numeric property and few observations from the start. Then we need to see if the data has what is the landscape of data, how many missing values does it have. So this vis.dat library and vis underscore miss command will show us a map. If I run it, it will make a plot. Let it open so that I can show you. So here you can see that it has made a diagram. So I'm moving it here so that it can be made bigger so that it is readable. So you can see there few variables which are in light color. There are no missing values, and the darker color shows the missing values. So so if you use the darker color variables, it will reduce the sample size. Okay. So this is the structure of the this is the what you call it, architecture of the data, how which one is missing, which one is not. Then you need to do is cross tabulations. Cross tabulation is used when you are comparing two variables which are in discrete nature. So I am comparing poor with, let's take some other variable which is more readable. So poor with gender. So what I do is I will write gen here. So when I do x tabs, what it will show that the poor is 0, 1 and gender is 0, 1. So a person who is poor and he is female, so 0 is for female. So there are 18,000 people. So poor and he's a male, so 16,000 people. Non-poor female for 54,000 and non-poor male 52,000. So you have separated the data into 4 types. So this is called cross tabulation. You can make more. Just copy it here and compare it with some other variable. So let's open the data file. Let's see if I pick the let's see, rather than if I see that if he has a master's degree, MS. So if I, rather than write Gen, if I say MS, master's degree. So you can see it here that it's not M, it's MAS. So if I run this, so it is showing us that the person is not poor, and this is showing a ratio. So there are very few people who got the master's degree, and most of them are poor. So this is showing a nature of a data. Now, first of all, we'll do estimate an OLS model. The command is fit equal to a linear model, poor and household size, and then data is going to fit. So what it is doing here is that it's only one variable. So if I run it, so it will store the estimation results. Then if I run summary.fit, it will give me regression estimates. So this is independent variable, this is slope, and so how 1 unit increase in household size will reduce the poverty by 0.02%, and it is significant. And the intercept is this much. You have the F statistics, which is significant. You have the R square, which is 3% only, because there is only one variable. The sample size used is, let's see, it's 14,100. It's 1,41,280. So this big sample size. So now we see if the regression is valid or not. So let's see. So I will do the NCV test. So it is showing us the non-constant variance score. So it's an heteroskedasticity test. So since the p-value is less than 0.05, so it means that it's it has non-constant variance. So what does it mean? It is saying us that let me clear the diagram. I can draw it here. So let's see. Okay, let me clear. So if I draw, so it means that if I draw x and y axis, and we have a data of the poor being poor here and h size here. So coefficient is positive, we already know. So what it is saying us that the regression line is telling us that it is positively sloped. So here 1 is here, which means not poor, and 0 is here, which means poor. So household size increase, there is a reduction in poverty. But if there is hetero, it means that data is mostly located at 2 points. So data is located at 2 points here, at 0 and at 1. So it is saying us that there is non-constant variance. What does it mean? That the dots scattered at the point 0 are nearer maybe, and dots scattered at the 1 are more far. So what does it mean? It means that the variance in the data is increasing or decreasing, or generally it means that the variance is not constant. It is increasing or decreasing or vice versa. So or any other type, that it is increasing first then decreasing. So this test is confirming that when the household size increase, there is a positive effect, that is confirmed. But the problem is for both samples, for non-poor and for poor, poor and non-poor, the variances are not same. So this means that there is heteroskedasticity. So let's do the next test. So it is CR plots. So if I draw this diagram, so what will happen is, since the data is big, so it will take time to draw this diagram. So you can see it here is that with the increase in household size, there is a change in is the residual plot has different values. So it is, if I draw a fit line on it, what is happening is it has a, what we call it, it has a positive slope, because there are fewer dots here and more dots here, so it is moving this way. Ideally it should be like this horizontal line. So this is giving us a hint that there is heteroskedasticity in the model. So why there is heteroskedasticity? Let me share the empty screen and let me give you a brief background, then we'll come back to it here again. So suppose you have data here, and you say that the independent variable is glasses of water that you drink, and here 1 means not thirsty and 0 means thirsty. So logically we know that there is a positive relation. The more the water you drink, the less thirsty you will be. So it should be positive slope. Let me take a straighter line. It should be positive sloped. But the problem is that when you estimate using this OLS line, it will draw a straighter line. What will happen? What's the problem with that? That it will continue forward or continue backward. So it means it will, if you estimate the y hat, it will tell us that the more you drink, it will go beyond 1. So it means you can be super non-thirsty, but in real life, you cannot be beyond 1, because you cannot be more not thirsty than not thirsty. Do you get the point? So the problem, it means that if you run an OLS model, it will predict more than one you want, but in real life it cannot be more than one. So it will create heteroskedasticity, because there are some values which are more than one here, and there are some values which are negative here, and it will create problems. So ideally the model should be, it's a sigma mod sign. So it is estimated like this. What does it mean? That when you are thirsty and you are drinking water, so your thirst is moving faster. So it is increasing returns to scale at the start, because you are very thirsty. Every glass of water that you drank, more thirst is removed. After a certain time, when you came here, it is decreasing returns to scale. So what is mean that when you are very less thirsty, the more you water you drink, the fewer thirst is removed, because you cannot be 100% less not thirsty anytime, and you cannot go beyond. So this line is drawn in a way that it will never touch 0, because at 0 you will die, and it will never touch 1, because at 1 you will never drink water again, because your thirst is removed. So at infinity it might touch at 0, and at negative infinity it might touch 0. So we are trying to estimate this model. So this is not linear. So what does it mean? It means that in reality the dots are following this bended line, which is expected, because when you're thirsty it is following increasing returns, and then you are not thirsty it is following decreasing return. But you estimated a straighter line. So what is happening? That at the start, so at the start, the variances are less than the line. At the end the variances are above the line. So variances, so let's call it v1 and let's call it v2. This is a variance. What is the variance? The distance of the dot from the red line. So v1 is not equal to v2. So this is causing heteroskedasticity, and this is shown in the error graph, that earlier dots are below and other dots are above with the residuals. So this is a diagram that explains why there is heteroskedasticity. So the first solution that we came to know is the use of Logit or Probit model. So Logit and Probit model does is they fit the non-linear line that we discussed earlier. So let's go and try to run this model. So for that we have to load following libraries. So this library name is AOD and ggplot. Okay, so let me estimate, run this line. So load the libraries. Okay, then what I do is I will run the logit model. So model of logit is GLM, generalized linear models. Poor household size, data is DF, family is binomial. So dependent variable is binomial. So when I run this model, to load the data, and then when I do summary, it will give me this answer. So it is showing that, so now coefficient is bigger as compared to previous case with the OLS. So but now interpretation is a little bit different. So if there is 1% increase in household size, or a 1% increase in household size, the chances of the individual to become not poor increases by 0.14%. I will write its interpretation here so that you can read. Let me write it here. So if there is one extra person in the household, then the chances of the person to be non-poor increases by 0.148%. So this is the interpretation of this variable. So hope it is clear here. Let me clear. Next is that it is giving us the sample, the median. So it is the answer, the center will not be at 0 because it's not a straight line. So this is the table. Now what will happen is we want that it should give us the confidence interval. So this command is connecting, it is binding two data sets, coefficients of the data and its confidence interval. So the regression coefficients are here. So now this is not interpreted like the way I did earlier. So its interpretation is, if there is one extra person, the odds of the person, if there is one extra person in household, the odds of that person to be non-poor increases by 1.16%. So when you use this coefficient command, it will give you odds ratio. Okay. Now, just like OLS, this model does not have the F test, so we have to create it. So this command will create the test value. Then it will compare it. It will calculate the critical, the confidence degree of freedom. Then it will test that test value with the chi-square distribution, and it is giving us the p-value. So this is the chi-square test of the model that I showed earlier, and it is significant, means overall model is fit. Then there is a log likelihood model. So this value is used when you compare two similar models. So this it will tell you how, just like a kite value in similar simple models, it will help you to compare different values, compare competing models. Then this was the Logit model. Logit model uses the nonlinear approximation of the data where dependent variable is between 0 and 1. Then there is a Probit model. It's also a competitive model, competing model to Logit. So M Probit, model of Probit is poor household size, degree, data file, and the model link is Probit. When you run it, it will give you the model. It has similar value than the Logit, and you can then compare its, calculate its odds ratio and the chi-square test, just like I did above. So these are two models. Now what I'll do is I will add another variable. I will add another reason of heteroskedasticity. So the another reason of heteroskedasticity is that your independent variable is ordinal, and you ignore it. Rather than you estimate in ordinally, you use it continuously. So I have introduced another variable in the model, that is education. So I will tell R that this data file dollar education means I'm calling that variable from the data file. So data file dollar education variable is a factor. It's an ordinal variable, not a continuous variable. So I will tell R that treat it as a factor. So when I use in Logit model education, what will happen is you will notice that it will make dummy variables for all categories in the education. So the education data was from 1 to 14. So it was a categorical data. But when I estimate, it kept education 1 in the intercept and estimated all others here. So what is happening is it is giving me the probability values of each household size. So here I think, let me see, the data file is showing us that 1 means poor and 0 means not poor. So you can see that increase in education is reducing the poverty. So the interpretations are, so let me do interpretation of this number. So if the education of the respondent is PhD, so 14 was PhD, then the chances that is not poor increases by 3.03%. So this is the way we interpret this variable. Okay, so let's move forward. So this model is there. Now what we want to do is we wanted to make a chart of it. So first of all, so since there are 13 variables related to education, we don't know what is the joint significance test, because there are 13 different p-values and one of them is insignificant. So what I will do is I will say vol test beta coefficients from the logit, and I will take from third to 15 coefficient. So if you see it here, so the third coefficient is education 2 and till 15. So it should be not, it should not be 15, it should be from third to the total is 14, 15, so it should be 13, 14, yes, it should be till 15. So there are total 15. When I run this, it tells me that they are overall significant. So education variable is significantly affecting poverty. So you can do these coefficient intervals, the odd ratios for all the variables. Since there are too many, it will take some time to load. So here you can see that coefficient odds ratio OR and its lower limit and upper limit. So this way you can interpret the model. I have already given you example. Now what I wanted to do is that I wanted to make a chart to show what is the effect of different level of education on the poverty. So I will, what I will do is I will create a new data file where I will use household size as the mean household size. So a mean data, and I will pick the education data from 1 to 14. So it will make a new data file where I will show you df1. So it has education values from 1 to 14 and average household size for overall data. You can see it's 7.99. So Pakistan, the average household size is around 8. So now you can see what I will do is add a new variable that is predicted value from the model. So we already did this activity to calculate y hat from independent variables. So what I'll do is I will pick these two as an independent variable and calculate the y hat. So predict mlogit model, use this data and calculate the responses. So what I do is it will create a new data. If I show it here, so this is y hat, this is education, this is household size. So when I go there, I can, so since now we have to make a chart. So I need to know what is the lower limit and upper limit of household size. So I will make a histogram here. So I notice that it starts from 0 to 20. Okay. So what I do is I will say that for each value of household size, so make a sequence from 1 to 20. Okay. And for each sequence, calculate 50 observations. So take 50 sample size. And for education, it will start from 1 to 14 and 100 observations each. So when I do it, it will make a data. So you can see that for each education, there are household size values. Okay. So then I will predict it using their data. So all possible combinations are there. Then I will calculate his upper and lower limit. So you can see it here that the commands are complicated, but you only have to remember what does it mean. So it's cbind means column binding, and df2 data, I pick the df data where household size and education data is there. Then I connected it, did the prediction using the mlogit regression command. The results are stored in mlogit, and then I said that also predict the standard error. Using that, I made a new data file df3 and I calculated the upper and lower limit. Okay, so this way I have, if you go in df3, you can notice is that there is independent variables y hat, standard error y hat, upper and lower limit, and the probability of that y hat. Okay, then what I do is I will plot that graph. It will start from here till here. So this graph will show us very useful insights. So hopefully it is understandable by you. So you can see it here is that by noticing the colors, okay. So here 0 means not poor and 1 means poor. So the 14 is in the bottom and 1 is somewhere on the top with 2. So you can notice is there, notice here is that with the increase in education, the graphs are going down. So higher education leads to lower poverty, and secondly it's positively sloped. It means that with higher education there is low poverty, but if you have a bigger household size, you have more resources, there are more demanders in the house, there are chances that there is more poverty. It means if you have 20 people in a house and there's only one person who is PhD, it means it not be able to feed other 19 people. So with an increase in household size, there's a higher poverty chances. So it's a three-dimensional graph where the third dimension is shown in terms of the color. Hopefully it is clear to you how this graph is made.